Because it's not like we're stuck in a corner with frontier models right now and we would have to like throw it all out of the window and start from scratch. I think pretty much almost any architecture can bring us to AGI. That's just one example. I think another one is really long horizon reasoning outside of text. Because it is far easier to learn reasoning from humans, but that way you're gonna be limited by human reasoning capabilities. And so an AI system should be able to do way better than that. When we're talking about robotics, I think the initial progress will come from, of course, a lot of data collection, maybe human data collection as well, and then web pre-training. So then that's the second way in which the world model can be really impactful, because with enough diverse pre-training and some fine-tuning on robot data, it can actually imagine or simulate the robot in sort of any scene that you can prompt the model to imagine. And so suddenly you can train your robot like in a million kitchens and trying to make a million different meals all in parallel in your data center.
What I see right now, a research community sort of divided. There are like big AI labs who are building, large language models using transformers and building products on top of it. And they're claiming that, okay, this is the path to AGI. And there's people like Ilya Satskover who basically saying that, okay, they lock themselves in that room, they're focused on research, trying to find other ways to how to achieve AGI. So I'm just wondering, what is your take on these different approaches?
I think there are different strategies. Like, it's clear that we have gotten a lot of things to work in AI and also that there are still capabilities missing. And I think, especially when it comes to dealing with really high dimensional inputs like multimodal models, there are still some things to figure out. When it comes to interacting with the real world, robotics, there are also still some things to figure out. I think, representation learning could be much better than it is today. Reasoning could be better, and just agents that execute long action sequences that really pursue goals for over a long time horizon and correct their mistakes. Of course, we can see this like starting to work a little bit. I think there's going to be a lot more to come there, a lot more capabilities that can be unlocked with clever ideas that we don't have yet. At least to me, the right path seems to be to start with what we have right now that works well and keep making improvements to it. Because it's not like we're stuck in a corner with like frontier models right now and we would have to like throw it all out of the window and start from scratch. To me, it's like what we have already is pretty amazing, and there are many ways to keep improving that without giving up those aspects of the current paradigm that are actually working really well. So I see all these capabilities getting added over time into really strong models.
Do you think that LLMs and in general transformer-based architecture can bring us to AGI?
Transformers are pretty general. I think pretty much almost any architecture can bring us to AGI. I think the actual architecture doesn't even matter that much at the end of the day. It's more like a compute efficiency question. Maybe it's a bit specific to what current hardware we have available. We could achieve AGI with transformers. We could achieve AGI with RNNs. Might be a little less efficient at training time, a little more efficient at inference time. Might need slightly bigger models to compensate for all the bottlenecks in that architecture. So overall, I think Transformer is already pretty good. There'll continue to be improvements to that. Yeah, I think architecture doesn't matter too much. What was the second part of your question?
If transformers and LLMs could bring us to AGI, but I guess you basically what you're saying is that architecture doesn't matter. What matters, what? Is it compute? What matters? What can bring us to AGI?
Yeah, compute, objective functions, data, some algorithmic aspects. Like for doing reinforcement learning, there are details that matter. I think we'll want longer term credit assignment than like basic RL at some point. And I would say, can LLMs get us all the way to AGI? The question is thrown around a lot. It's actually interesting to talk about it because, what is an LLM? What we have deployed at Frontier Labs as products, they're not even just LLMs anymore, right? They have image understanding, they have image generation now, video understanding. Maybe video generation is still separate, but it's soon going to be part of that too. So we're already way past LLMs, actually. There's no question of whether LLMs will get us all the way there. So I'm glad you asked that question because I feel like it's on a lot of people's minds. And I just want to like point out that we're already past LLMs, and there's no debate even about that anymore.
So basically, when I interact with Gemini or Claude or ChatGPT, I'm not only interacting with LLM, I'm interacting with very complex multimodal system.
Yeah, exactly.
And you also mentioned earlier that we need some clever ideas for AGI. I'm just wondering what clever ideas were missing today, in your opinion?
So I don't know the exact ideas, right? I think there are some clear open problems we still need to solve. One of them is really long context understanding. We have models with 1 million tokens context or more. For video, you would want a lot more than that because video has so many tokens. Even for text, the retrieval and really reasoning based on taking all that context actually into account is not quite there yet. I guess I don't know what the solution is going to look like exactly. There are a couple different approaches based on maybe retrieval or hybrid models that learn some sort of state representation, but they also do some attention. Maybe like associative memories that are a bit like a transformer, but not attending back in time necessarily. Yeah, honestly, there are a lot of cool ideas in the literature that came out before transformers. I just think a lot of those have merit. They were just too early. Like what mattered at the time was not really long-term memory or some fancy addressing mechanism, but it was just scaling up and having a compute-efficient architecture. That's just one example. I think another one is really long horizon reasoning outside of text, because it is far easier to learn reasoning from humans, but that way you're gonna be limited by human reasoning capabilities. And so an AI system should be able to do way better than that if you put the right algorithms into it that would allow it to discover reasoning by itself. And so then you have to figure out how to extract concepts that are maybe abstract in space and time from like raw data, maybe high dimensional, like video, audio data of people living their lives, eventually maybe data of a robot that's living around people. Yeah, abstracting concepts and then maybe planning over them in some way. I don't think we have a great handle at how to do that. And it's not clear that we'll be able to get that to work in the next few years. But I think once we do, it'll be really impactful.
We're moving towards continual learning conversation. And actually what you said, it reminded me, I recently spoke with Tommaso Poggio. He was a mentor of Demis Hassabis. And he said in 2015, Demis was saying that to build general intelligence, it's 80% neuroscience, like 20% engineering. So recent update from Demis is that I'm not claiming the correct quote, but it's basically something like maybe 90% engineering, the rest may be neuroscience. Basically, when you said that we need different type of reasoning, different from human, indeed, we creating different type of intelligence. And maybe like comparing with how human brain works, maybe incorrect, right? Because it could be like very different beast and more powerful. To the point of continual learning, and I guess, as I understand, your research work with Dream 3, and like this is the attempt, right, to enable continual learning.
First of all, I like the neuroscience comparison. I do think neuroscience can teach us a lot. It's just, there's so many different ways to approach neuroscience, and you could do it at like a really low level of modeling continuous time, like neuronal dynamics. It gets very expensive and inefficient and hard to actually train a scalable system. I think if you actually take all the constraints into account, the brain is pretty big. If you do neuroscience and you want to build a model of the brain, better be pretty big. And then it makes sense to start simplifying certain concepts for compute reasons. And maybe in like 30 years from now, we have the compute that we could do it at the low level. We could see if that gives additional benefits. There are so many things that we can improve right now in like quite obvious ways through engineering. And these systems are so massive in terms of compute and distributed computing that a lot of engineering is necessary. And there are also so many details where no intuition can help you. You have great intuition about how the brain learns or just some algorithmic idea, but now there's like 10 details you just have to like try out, be really careful about, compare hyperparameters. So it's a lot of experimentation and engineering. But that's not to say that there's no merit in neuroscience. Like, I think since we've been pushing the engineering so far recently, I think actually there's more and more value in going back and getting intuitions from neuroscience. And continual learning is one of them. It depends what environment your system is embodied in for continual learning, right? So you can already do maybe some amounts of continual learning in text land from deployed chatbots interacting with users. And it's an interesting environment. It's a very dynamic environment. You can learn new knowledge by talking to people, but it's still like very limited compared to a human actually interacting with the real world. That type of continual learning, I think, is still quite far. And it's not necessarily addressing any current bottleneck, I would say. When we're talking about robotics, I think the initial progress will come from, of course, a lot of data collection, maybe human data collection as well, and then web pre-training. And a lot of that will be video data. I think that's where sort of the biggest improvements will come from in the next few years. And then we can worry about continual learning at some point to squeeze out more robustness and work on the long tail. I think with Dreamer, I've tried to solve different problems with different Dreamer generations. So up to Dreamer 3, it was really all about learning from scratch by interacting with some environment and making it really data efficient. And then also pushing the final performance that you can achieve. Because up until Dreamer 2, model-based algorithms let you learn very quickly, but then they would sort of max out. Whereas a model-free approach would need a lot more data to learn, but it's just has a higher ceiling. Whereas then with Dreamer 3, we actually got to the point where we can pretty much outperform any RL algorithm out there, and also make it robust to the point where you don't have to tune hyperparameters. And we had the Minecraft Diamond Challenge, like train or learn to get diamonds from scratch, just from sparse rewards. Whereas with Dreamer 4, we did exactly the opposite and said, wait, no, we know how to learn online now. How about learning offline? You also want to be able, just from a data set you have, to extract as strong as a policy out of it as you can in situations where, it's dangerous to interact with the environment. And so then it's like, what if we only have this fixed data set of only human data, right? And nothing else? Can we learn to get diamonds from that? And then, of course, neither of those is a perfect solution. It's just addressing one specific problem in an isolated experimental setup. But in the future, of course, you throw all those things together.
I was just curious. I've come across this. I've been looking at this notion of nested learning models or nested training models. And, what they do, in my view, that's interesting is they take the context and they make it into a neural model so that the context is actually learned quickly, even in a GPT type thing. It's not really a GPT anymore if it's a nested learning. You can wire the context instead of keeping it external into the neural model. And that seems to me to be a pretty interesting thing to do that shifts some of what you were talking about. And I was just curious if you had anything to say about that.
Yeah, I think it's like a sort of parameterized memory approach. I don't know the exact algorithms you're talking about, but
this is the notion of having one portion of the neural architecture of the GPT, or whatever you want to call it, that is actually allowed to learn quickly from the input, so that the context is being built dynamically. I mean, most GPTs, they absorb the context at inference time and then they throw it away. There is no ongoing learning. It's a fixed static entity. They can't learn from the context because the context passes through them at inference time and then it's gone. Nested learning, as I understand it, devotes a portion of the neural architecture, of the network architecture, to essentially quick training on the context as it's being input, and the context can be as large as it is, so that is, shall we say, adjacent and retained throughout the conversation within the model.
There is a line of work on training some really small, lightweight part of the of the architecture at inference time. I think that's an interesting approach. It's sort of, what I like about it is this. When you train a neural network, you're optimizing it with an objective function, right? And so therefore it'll get better as you train it more. And then in context learning is this totally different mechanism where you just hope that the model has learned to generalize in a way that looks like learning, but there's nothing built into the system that would really make it aggressively optimize any objective, really. It's not trying to be really good at remembering. It's not trying to be really good at trying to understand the patterns in the context in a way that helps it predict what'll... Like, we can try to get all of these things into the weights during training time by constructing clever training examples that force the model to solve puzzles and remember things and so on. But it's still going to be a learned algorithm at the end of the day. It may not be as goal-directed as if you actually do an optimization procedure.
You can't optimize an inference time, obviously. And so no amount of pre-training is ever going to anticipate what is going to come and be introduced into the context at inference time.
That's right.
Is the model simply a passive inference engine that you pass the entire context through each inference, or does the model in this session develop an awareness, shall we say, of the context?
I think it's a cool direction. I share the intuition that just learning the in-context learning as an algorithm, like we typically do, is likely not going to be enough to build the most powerful systems. There's one way to solve continual learning, which is just to say, of course, there are all these different ways to make it more computationally efficient at inference time, and I think that does make a lot of sense. But also, I think at some point, we're just going to keep training the model as it interacts with the world. If you have millions of users, maybe you'll batch like 10,000 user interactions together and you do an update on it, and then the model will actually deeply learn. And then there may not even be the necessity to have a different timescale of learning in that sense. But it's also possible that, we do want multiple timescales of learning for efficiency. And so then there might be like a quite general way to just make an algorithm where you can say, I want k equals 5 learning timescales now. The faster timescales will be more efficient to train. I could see some generalization like that as well. Yeah, I don't think we have any algorithms in that space yet that actually work well enough to truly be worth it in production. But it's a very interesting direction. And yeah, I totally agree with continual learning being important. To me, it seems like it's all a question of how long the feedback loops really are, right? Because let's say GPT-4 is released and interacts with the world, and of course, OpenAI gets a lot of data from those interactions, and that'll influence GPT-5 for the next training run. But that might be like a year or two later. Can we get that down to maybe days or maybe even seconds?
Can we reduce that gap of instead of 2 years, bring it to a gap of 10 days?
Yeah, I think that's a continual learning question. And we definitely, in theory, can. I guess quite hard to experiment with that at large scale because training run of a big model is so expensive. And then making sure that the model stays safe as you do that. There's a lot of benefits of just having a static model because it's easier to study. It's hard enough to figure out what kind of quirks the model has and how to patch them. It is a challenge, but yeah, I think eventually we'll shorten that feedback loop over time.
You mentioned that, we need better objective functions. I just wanted to touch base on that. Can you elaborate on that? What do you mean, better objective functions?
At a fundamental level, there are 2 types of objective functions. There are preferences, like rewards, or inductive biases, those kind of things that we as humans have to specify because there's not really much of a mathematical structure to them. Our preferences are shaped by society and our experiences growing up and all that. So there's no equation that can describe them. You sort of have to learn them from data, from human ratings, let's say, or human feedback. And then there are information-based objectives that try to make sense of the data available, right? Like a prediction objective, try to predict the next token. or a masked autoencoder that learns representations, or for an agent, even a curiosity objective, where the agent tries to seek out information in the environment, let's say. Probably on both fronts, actually, there's good room for improvement. And we have really powerful optimization setups now, right? Our architectures learn very efficiently, and we have great optimizers. A lot of engineering that went into building these scalable systems, just at a systems level, that, data and objectives becomes quite important. I think for text, you can get quite far with next token prediction, but also there is a lot more you can do. Like, for example, there are clear benefits of predicting multiple tokens at once. It tells the model, it trains the model to be a bit more foresighted. Then when it comes to multimodality, there are so many. Right now, it's still just like a patchwork of different objectives. Maybe we use like a contrastive loss for the vision encoder, and the next token loss, next token prediction softmax over some interleaved like text and image tokens on top of that. And then maybe there's a diffusion loss to generate images of that model. We have to balance all these losses. I think there's probably like ways to unify everything that makes our lives simpler and also ends up giving us better performance in the end, right? Because there is a benefit, there's a reason that, let's say, one loss works better for one modality and another one better for another. There are benefits to that. I don't think those are like fundamental trade-offs. It's just if we can abstract away from everything, we'll be able to share these benefits across the whole spectrum. And then when it comes to building agents, I think there's like a huge design space of, I think short-term RL, like learning tasks up to maybe like 1,000 time steps or so, works really well and robustly now. But training, like solving long horizon tasks, optimizing them end to end, is still not working that well. Just accumulating errors at each time step. Yeah, I think there's still a lot to explore there in terms of just improving end to end RL. And then after that, maybe figuring out like exploration objectives, goal reaching objectives, how to learn robust reward models in a general way. The only thing that's missing for those things is basically objective functions. You could say we don't have the data, but honestly, like we have the data that's there, and anything that you can collect manually through humans is also not that hard to collect. So it's really about having an idea of like how to build a system like that. We have done so much scaling and data engineering that we've gotten quite good at that. And we shouldn't like stop doing that, but it's just like not that hard anymore. And now we're back to figuring out algorithms.
I mean, you work also on embodiment, right? And that's also like the core of your research, but it's like your research interest. And I'm just wondering, in terms of embodiment and like physical interaction with the environment, is this like crucial for more efficient world models? Like what's your take on this, like when it comes to interaction with the physical world and building general agents?
So when you train a world model on a fixed data set, then it'll be limited in certain ways because there will be counterfactuals that it just has never seen. And we noticed that for Dreamer 4 in Minecraft, for example, is only trained on human data. In the game, there are maybe like 5 different pickaxes that you can make. There's like a wooden pickaxe, you put 3 like planks there and some sticks. There's a stone pickaxe, you put 3 stones and some sticks. And the human players know that. So they never try to make a pickaxe out of some other material. But the RL agent does. And so then the world model is like, I don't know. It looks like they're making a pickaxe. Maybe I'll like give them a pickaxe, even though that recipe doesn't actually exist. There is definitely a limit to how far you can go just from offline data. Then the good news is that we found that with not too many rounds of getting corrective data from the environment, those issues actually go away very quickly. I think there's actually an important interplay between an RL agent that optimizes against the world model and finds all the potential flaws, and then deploying that in the actual environment, getting feedback for which of those things worked and which didn't. And so it's an adversarial game where at the end of it, the world model will be very robust and you'll have a really strong policy. At least in Minecraft, after 2 to 3 rounds, we didn't see those exploits anymore. In the real world, it might be a little more. But yeah, you have to unless you have a perfect data set, which I think in the real world will just not be it'll not be possible to construct that upfront. So then you just have to interact with the environment to figure out a real causal model of the world. Once you have that, maybe then you have the data set for the next training run. it might be fine to just directly train on that.
Have you scaled your world models? I'm just curious to see like how they behave agents at scale.
Yeah, we definitely have. So these are also all results that we didn't put in the paper, but there's already too much in there. Yeah, we did scale up all the way to like the same size as frontier video models, and it works well. Yeah, I mean, with the architectures we have now, which are basically very efficient diffusion forcing video models and the robust RL objective, you can scale very easily. Like it's just a question of how much compute can you put in really, and like how many thousand chips can you pull together and train a big model.
Have you seen any like interesting observations like in the behavior of agent when it's like scaled? I'm just curious. Like,
yeah, you sort of see all the same like emergent behaviors that people were really excited about for LLMs a while ago. And I think it's just, since by default the world model is just an unsupervised objective, you're not telling it what parts of the data to put its capacity to. The model sort of decides based on its inductive biases. And so then, if your model is too small, for example, inventory predictions would not be very good. And you could specifically collect data for that. And we tried that too, and it definitely improves that. But another way to do that is to just scale up the model. Make it like 8 times bigger, and it starts to get really good at inventory dynamics, especially if you have like a little bit of this corrective data that we had lying around from previous runs. Yeah, basically just the model gets sharper at everything, the bigger you make it. And of course, then we did like full, YouTube pre-training runs as well, scraped big data sets and filtered them for quality and trained on that. And that's when you really get like strong generalization benefits. Yeah, unfortunately, it's a little challenging to publish a lot of this like more really cutting edge stuff. Yeah, I think scaling is going very well with these models. And especially actually, I would say, I think the ceiling for scaling of video models and multimodal models is way higher than for text models, because there's so much more information in video. Even top video models are basically underfitting, right? Of course, they are sort of a bit collapsed down into like very pretty cinematic clips, and that helps the model, even though it's not as gigantic, to still make really nice generations. If the goal is not just to generate nice videos, but actually to like have a rich understanding of the physical world.
Of physical world through those videos.
Yes, and maybe through some like robot data or data of humans interacting with the world, pre-training like videos from the internet. So if the goal is to actually have a deep understanding of the world, which is like more relevant for maybe robotics and interactive assistance, as opposed to the goal being more like creative applications, like generating video clips for movies and so on. So if you want this general type of video model, then yeah, I think the scaling ceiling is going to be like at least an order of magnitude higher than what we see for text models. So we're not even close to that right now.
Interesting. So we can continue scaling like video data and extracting more and more knowledge from it, right? What capabilities in models you expect from that?
It's hard to make a guess, but one goal there is, of course, to get transfer across modalities. I think the most obvious is just going to be have representations that are really good just at understanding the world. To predict forward, you have to know, to predict how an object is going to move, you have to know its mass and its friction and like how it looks like on the other side, because maybe it's going to rotate, and how objects interact and how people interact. I mean, there's a lot to extract there in terms of representations. And we've seen those representations be really strong for then fine-tuning policies into them. And I would imagine they are probably really good representations also for maybe reasoning tasks about the real world, especially if you have some context of, you show on the phone, you show your agent something.
Would it be transferable to robotics? I mean, now, like, as I understand it, in robotics, like imitation learning is main technique that brought those advancements. I'm wondering if like this richer representation also transferable to robotics.
Oh yeah, 100%. That's actually, there's a lot of leverage for representation learning techniques on imitation learning performance, right? If you train your policy from scratch, it's going to take a lot of data and you'll get a pretty fragile, narrow policy that only works in that specific scenario. If you start with like a pre-trained VLM, you can do a little bit better. But those representations are still not really the right ones for understanding the world at a physical level, at a level that matters for control, like precise object locations and physical properties of objects, like how slippery is this plate if I pick it up? If I like pick up this cup at the handle, how firm do I have to hold it for it to not just like slip out of my hand, for the tea to like spill over all over the table? Like those representations are very natural to get from some sort of like video prediction model. It doesn't necessarily have to be the fusion model, since it's mostly about the representations that are being learned during pre-training. But those representations we already have seen work massively better. And so I think just scaling up general video models will be, the very first way in which we'll just see that be really impactful for robotics is through their representations. And then in DreamUp 4, we showed the whole recipe for how to fine-tune a model like that by adding agent tokens to train a VC policy and then train a reward model and then RL fine-tuning. So then that's the second way in which the world model can be really impactful, because with enough diverse pre-training and some fine-tuning on robot data, it can actually imagine or simulate the robot in sort of any scene that you can prompt the model to imagine. And so suddenly you can train your robot like in a million kitchens and trying to make a million different meals all in parallel in your data center without having to like rent a million Airbnbs and produce a million robots and move them around through the city. Doing that at scale is a little more challenging, but I think that's like the second step change after the representations that we'll see in robotics.
I did take a scan of both of your papers. A number of things are kind of gaps in my understanding exactly what's on, but a few things are interesting. One thing in the language models is there seems to be sort of a quality difference, what they can learn and how they learn it when you look at pre-training versus reinforcement learning. Pre-training tends to learn more factual stuff, and reinforcement learning tends to not be so good at learning the fundamental domain principles, but once you have a pre-trained model, it can be really quick in developing new skills. So when you put those together, I think there's, a lot of interesting conceptual things to think about.
I think certainly learning knowledge from examples rather than rewards is a lot easier, right? Because for rewards, for reinforcement learning, you have to first guess the piece of knowledge and then the model will be told whether the guess was correct, right? So it's a lot less efficient for just absorbing information. And then reinforcement learning is really good at, refining your strategies, because it's hard to get like optimal control data in any way, right? Like let's say you have an LLM agent, it's actually really hard to get a data set of, what is the optimal next step to do right now. Good luck. Humans are not anywhere close to optimal. And if you collect with contractors, like you have to do, you probably have to discard like 99% of your data, and optimality depends on your horizon as well. Ideally, you want it to be optimal for a really long horizon. So it's very hard to get data for that. And so that's where reinforcement learning really shines. Plus, once the model is already pre-trained, it has learned some decent behaviors. There's a lot less to refine at that point. It's really sort of just doing a bit more of these things that work well and a bit less of these things that are not so efficient. I think it's the same for humans, right? We definitely learn things from observation by just trying to predict what's going to happen next in some way. And that's our way of absorbing knowledge. And then we also learn from trial and error. We do something, it's like, oh, that didn't work out. Oh, this was really great. And so we learn our skills, reinforcement learning. And I think there's a little bit of skill learning, sort of very broad but sloppy skill learning that happens from observation as well. And so I think that's just generalization, because we predict what other people will do when we watch them do something. And our mental concepts or representations of other people are not that far from the representations of ourselves. And so then we start to be able to envision ourselves doing those things as well, just by nature of, training a system on all that data and having it generalize.
Also, a very interesting additional opportunity when you are doing both of these simultaneously, as opposed to learning prediction first and learning reinforcement learning, in that it changes the world distribution that you're predicting. And there's an analogy there. Expert in a particular area, let's call it a physical embodied area, notices all sorts of details that a person who doesn't work in that area would never even pay attention to. We haven't seen that as being an opportunity to take advantage of that in the language model space very much.
Yeah, it's basically this idea of agents finding their environmental niches. You converge to a distribution where you can achieve your goals reasonably and you can predict what's happening reasonably. Your system is less likely to fail, right? Because it's practiced exactly on that data. And it's also allocating all its model capacity to that relevant distribution. So it can start to forget other things. Another way to build a more powerful system is to just make it bigger and train it on more data. And so you're growing the niche. But then there'll still be sort of corners where, at the edges of that data distribution, the model will fail a bit. And I think that's what we're seeing with LLMs at the moment, right? They're like pretty general and pretty good at most of the in-distribution stuff. But then there are these like sort of edges, the boundary of the distribution where they get tripped up and like misgeneralize and hallucinate maybe, and doing some sort of online RL would help really like refine the system in a way where, if it hallucinates, it'll get a negative reward because the user wasn't happy with the response. And so then like either it learns what the right answer would be, or it learns that it doesn't know the answer and it's better off just saying, I don't know, and ending up in like a very solid distribution.
I'm also wondering, like you mentioned earlier, the way, as I understand, this is going, and you said that, okay, we have like very performing systems and we will keep improving on them and we will have more and more powerful AI systems. I don't know if we call it AGI, because it seems like there's lots of debate, like what is an AGI, but it seems like this will be very, very powerful. We might have this continual learning progress because people working on it, right? And at some point, maybe there will be some new interesting developments. How do you envision this future in the next maybe 10 years? I don't know, like if it makes sense to speculate, how you think things will unfold. We will continue with keep improving this current AI systems. And if something like comes up, like new interesting algorithm, it will naturally converge together, or it might take like very different direction.
I think the field is way too connected for things to really diverge. I just see things coming together more and more. With the expense of training big models, it only makes sense to have one training run and get one model that can have all this cross benefit and share one like compute check, one training run. Agents are already becoming part of deployed frontier models. Video generation, mostly separate still, but I wouldn't be surprised if maybe in a year from now we had strong omni models that go in all directions and also generate video with the same weights. Of course, there are some challenges, but yeah, in terms of bigger picture, I think that's all solvable. And I think this like learning to reason seems like pretty challenging conceptually. We don't really have a great idea for how to do it. So I could see that taking more like 5 to 10 years maybe. Robotics could make good progress even towards like a useful like sort of general robot product, the first version of that, in maybe 3, maybe 4 or 5 years or so. So I don't think we necessarily have to crack this like really complex long-term reasoning to make something useful there. Yeah, I guess that's like a couple predictions there.